Hello, everyone. I'm Nara. I recently graduated from UC San Diego and now work at IBM Research Almaden. Today, I will be presenting our work on DPUF done in collaboration with my advisor, Steven Swanson, at the Non-Volatile Systems Lab and my colleagues at IBM Research, Daniel and Swami. Now, let me start my presentation on DPUF, a DPU-accelerated near-storage secure filtering. As data volumes grow exponentially, more organizations are using data lakehouse solutions to efficiently query massive data sets. These systems store vast amount of data in columnar formats like Parquet and leverage cloud object storage for flexibility, scalability, and cost efficiency. However, as the storage and compute are decoupled, querying large data sets stored in the cloud often leads to network bottlenecks due to the need to move data over slow network flow processing. Actual studies on analytics workload show about half of queries touch less than 1% of the data, and Azure reports applications often use under 20% of what they read, making much of the data movement and transfer unnecessary. Filtering this data using analytics compute memory is not only inefficient, but expensive. The intuitive way to solve this problem is to push down the computation close to storage. Prior solution of filtering pushdown is Amazon S3 Select. This allows for simple SQL queries be processed directly on formats like CSV, JSON, and Parquet stored in S3 using storage nodes limited CPUs. Another approach is near data processing using smart SSDs, which integrate processing capabilities within the storage itself. However, this approach faces significant integration challenges and is limited in flexibility, scalability, and visibility. Moreover, both approaches have a shortcoming. They are impractical for use with sensitive encrypted data, as these techniques would require access to client encryption keys, compromising data security. When dealing with sensitive data, users tend to encrypt the data with their own keys before storing them in cloud. As a result, we are forced to fetch entire objects from storage to decrypt and process, even when only a small portion of the data is needed. To address these challenges, we present DPUF, which securely filters sensitive data close to storage using a DPU as a secure enclave. First, let me give a background on DPU. The DPU is a system on a chip. For instance, the NVIDIA's BlueField 3 has 16 ARM cores, 32 gigabytes of DRAM, storage, and hardware accelerators for tasks such as encryption, compression, and regex matching, and can be connected to the server through PCIe slot. BlueField also includes secure boot and implements zero trust security models. DPU is designed to offload tasks from the main CPU, particularly network and security workloads. However, in this work, we extend the DPU's capabilities for large-scale data processing. In DPUF, we use DPU as a secure enclave. DPUF uses secure boot and remote attestation to ensure only verified software runs, while the DPU's architectural isolation from the host provides a trusted partition that protects sensitive operations and client keys. Within this trusted boundary, we introduce a fully optimized and modular data filtering pipeline. The pipeline decrypts data, evaluates filtering conditions, encrypts it back, and returns the query results, ensuring minimal data exposure. Although the DPU has built-in crypto acceleration for decompression tasks, its limited compute and memory mean that achieving high throughput requires careful memory management, efficient task scheduling, and tight coordination across the DPU cores and its accelerators. Now, let's look at the scenario that DPUF targets. The data resides on the storage server that exposes a standard S3 or REST API. This server holds large encrypted Parquet objects that clients need to access. The server is equipped with a DPU, which is configured to have its own IP address and presents an S3 Select compatible interface. It listens for incoming requests directly from clients. And when the client issues a filtering query using S3 Select, the DPU receives the request, fetches the encrypted data from the local storage server over a high-speed PCIe link and performs decryption and filtering directly on the DPU. Only the filtered result is returned to the client over the slower WAN link. This reduces data movement and requires no changes to either the client or storage backend software, making DPUF seamlessly integrate into the existing infrastructure. To operate efficiently within the DPU's limited compute and memory resources, DPUF applies several optimizations. First, we use chunk-based processing. Large data sets are split into smaller chunks and fetched in parallel to saturate the bandwidth, while keeping the data to fetch within the DPU's limits. Second, we reuse pre-allocated DMA buffers across the pipeline, eliminating setup costs and keeping the crypto engine easy. Third, DPUF processes packet data incrementally at the row group level. A row group is simply a block of rows, which helps bound memory usage. Each row group is decoded into arrow, and processing is parallelized across cores. And finally, we tune the crypto stage by reusing task objects and use polling-based scheduling to minimize delays between operations. Before diving into system-wide performance evaluation, let's first look at the decryption throughput across different compute backends. On the left, we see software-based decryption on a typical x86 server and on the DPU's ARM cores. On the right, we will see throughput on DPU's crypto engine. Both software-based decryption of 400 megabyte data deliver around 3.3 gigabits per second, not enough to keep up with the line-range data access. One thing to note here that DPU's power-efficient ARM cores are as performant as the host server CPUs while being more power-efficient. Next, we show the peak throughput of DPU's hardware crypto engine of 74.6 gigabits per second, measured on a small 2 megabyte input. But for larger real-world objects like 400 megabyte files, the baseline throughput without optimizations drops to just 13.2 gigabits per second, leaving a large performance gap. This is due to the crypto engine supports single 2 megabyte data decryption task at the time. Through our optimizations for registering buffers, reusing task structures, and using polling-based scheduling, we closed that gap significantly, achieving 62.4 gigabits per second on 400 megabytes of data. That's a 5 times improvement over the baseline and nearly 20 times faster than software-based decryption on the host. Now, let me evaluate our work. To evaluate DPUF, we use the TPC-DS benchmark, focusing on encrypted and unencrypted data filtering. We extract, scan, and filter fragments from TPC-DS SQL queries, similar to how engines like Apache Spark decompose queries to isolate just the filtering logic. For encrypted filtering, we compare DPUF against client-side filtering. For unencrypted data, we compare DPUF to S3 Select. Our testbed includes a client and Bluetooth 3 DPU connected via PCIe to a MinIO storage server. First, let's start with query latency. The following graph shows the query latency under different network bandwidths ranging from 50 megabits per second to 100 gig per second. The blue line represents traditional client-side filtering. As you can see, the latency is extremely high, especially at lower bandwidths, because the client has to fetch and decrypt the entire data set on the client side before filtering. The yellow line shows DPUF performance with average selectivity queries. Since filtering happens on the DPU, we avoid transferring irrelevant data, which significantly reduces latency across all bandwidths. Now, the red line shows DPUF performance for highly selective queries, where only a small fraction of the data is returned. Here, the latency is consistently low and almost unaffected by network bandwidth thanks to the minimal data transfer. Overall, DPUF shifts the performance bottleneck away from the network and achieves much lower, more stable latency compared to the client-side filtering. Now, let's look at the unencrypted data filtering, where we compare DPUF against S3 Select. Here we will show end-to-end latency for running a query over the network bandwidth of 400 megabits per second between client and server. We compare 5 setups: client-side filtering with 1 core, S3 select, client-side filtering with 16 cores, and DPUF with 116 cores. Client-side filtering with a single core is extremely slow, nearly 500 seconds, since it fetches and decrypts the entire data set before filtering. S3 select improves performance by pushing filters to the server, but still much slower than DPUF, taking around 150 seconds. Even with 16 CPU cores, the client-side filtering still takes over 57 seconds, while DPUF with just 1 core already reduces latency to 7 seconds. And with all 16 DPU cores active, we bring it down to just 1.4 seconds. That's a 350 times speed up over single core client-side filtering, 41 times over 16 core client-side, and 109 times faster than S3 select. In this work, we presented DPUF, a system which accelerates time to insight by uploading the filtering post storage to a DPU and transmitting only the relevant data. And DPUF enables secure, large-scale analytics with lower cost and resource demands. Please take a look at our paper for more details. And thank you very much for your attention. And I'm ready to take any questions.